All right, it is 2 p.m., so let's begin. Hope you guys are having a good day. First thing that we're going to talk about today is basic circuits terminology. So before we can begin developing techniques to analyze circuits, we need to make sure that we're all kind of speaking the same language and so that we're all on the same page. So the first thing that I'm going to do today is to introduce a generic circuit element. So this is going to be our symbol for a generic circuit element, and I'm going to call this guy element A because it helps to label things sometimes. This circuit element is an example of a two-terminal element. So the terminals are these guys right here, and the terminals are what allow us to connect additional circuit elements to this guy. Okay. Not all circuit elements have two terminals. In fact, later on in this class, we're going to be dealing with multiple circuit elements that have much more terminals. The operational amplifier, how we deal with it in this particular class, we will treat it as a three-terminal element. But later on, depending on how advanced you get in circuits, it could be treated as up to a seven-terminal circuit element. Okay, so this two-terminal circuit element is fairly representative of an awful lot of the different types of components that we're going to be dealing with in this class. So the two-terminal element could be a resistor, a capacitor, an inductor, a battery. Really, there's an awful lot of things. But before we get into any specifics, I just want to kind of lay out some ground rules here. So as I said previously, a circuit element's terminals are what allows connections between elements to be made. So if I wanted to introduce another circuit element into this system, let's call it element B, I would simply connect the two circuit elements together by connecting a set of terminals like so. What this has done has created a network. Okay. So let me define this. A network is an interconnection of two or more circuit elements. And another definition that we can introduce right here is that of a node. Okay. So a node is a point of interconnection between two or more circuit elements. So in this particular network that I've drawn here, where we have element A connected to element B, there is a node between these two elements, which I'm filling in right here in pink. That's one way that we can identify a node. Another way, and one that I prefer, is we would start by drawing a line between the two elements, and when we reach the next, circuit element, we turn around. So this whole guy, these whole sets of lines represents one single node. And the reason why I like to draw nodes in this way will become pretty obvious in just a second, okay? So let's continue on and add a few more circuit elements to our network. So let's call this guy C, and let's call this guy out here D, and let's connect these guys together. So adding these two extra circuit elements have also added a couple of extra nodes. And we can see that we now have a 3-node system. Okay. The way that these elements are connected is important. Okay. So let's look at the connection between elements A and B. We consider elements A and B to be connected in series, where a series connection is a connection between two circuit elements with no additional branches. Okay. So when we only have a single point of interconnection between two circuit elements and there's no other branching paths, which is exactly what's described by this node that I've highlighted in pink, those two elements are said to be connected together in series. If we look at elements C and D, we can fundamentally describe what's called a parallel connection. In a parallel connection, we have a connection between two or more circuit elements where both sets of terminal pairs are shared. And so let me explain exactly what I mean by that. The top terminal for element C and the top terminal for element D are considered to be shared because they're connected to the same node, which I've highlighted in green. Similarly, the bottom terminal of element C and the bottom terminal of element D are shared because they are connected to the same node, which I've outlined in light blue. So because the pairs of terminals are shared, elements C and D are considered to be connected in parallel. Now, it's actually very important that we realize that not all connections have to be series or parallel. For instance, if we look at the connection between elements B and C, we can't say that they are in series because while there is a single point of interconnection right here, there's also this branching path. So that's what makes them not connected in series. The reason they're not connected in parallel is because while they do share terminals at the green node, they don't share the other pair of terminals, right? The left-hand terminal of B is connected to the pink node, and the bottom terminal of C is connected to the blue node. So that terminal pair is not shared. Therefore, elements B and C are not in parallel. This is actually a point where some students typically get confused. Maybe it wasn't explained well in your engineering 120 class, so that's why I'm kind of trying to go through here. So does everybody understand the difference between a series connection, a parallel connection, and that not all connections have to be series or parallel?
Would you say that elements A and C are in parallel with each other?
So A and C are not in parallel because while they do share the bottom terminals, right? So the bottom terminal of A and the bottom terminal of C are connected to each other. The top terminal of A is not connected to the top terminal of C.
Okay.
So because A and the top terminals aren't connected to each other, they are not in parallel. That's a great question.
Thank you.
Any other questions? All right, well, let's move along, and I'm going to erase these node things real quick, or try to. So we can talk about another topic relating to this little circuit here, or network. Maybe drawing it bigger. All right, let me redraw the things I accidentally erased. All right. So the way that I've drawn these circuit elements have introduced closed paths in our system, okay? And so that leads me to another definition. A circuit is any network that contains at least one closed path. Okay, and further, we can define a loop to be any closed series of circuit elements and nodes. So if we look at this circuit that I've drawn here at the top, how many loops do you guys think that this circuit contains?
2.
2. Okay, that's a fairly good guess, but it's actually incorrect. And the reason why it's incorrect is because a loop is any closed series of circuit elements and nodes. So let me explain why the answer isn't 2. Let's start with this guy right here. Hopefully it's fairly obvious. This closed path we'll consider to be loop 1. Somebody is saying 4 and somebody else is saying 6. I disagree with those answers as well. Elijah says 3. That is an answer I do agree with, and I will continue explaining why the answer is 3. So our first one is just around that one little, we'll call it a window pane there. And then we have a second one similarly here. That's probably the 2 that the first, Harrison, I believe, said that there was any closed path counts. We can also consider this guy around the perimeter as a loop as well. So there is our third loop. I would be interested to know where the other ones came from, but it's not that big of a deal. So does everybody see that there are three distinct paths, or three distinct closed paths? Therefore, there are three distinct loops in this circuit.
Yes.
Okay, so I'm going to introduce one more little definition here, and that is what's called a mesh. A mesh is defined as any loop which does not contain a smaller loop. So in this case, loops 1 and loops 2 would be considered meshes because they're the smallest possible loop that don't contain any other loop, whereas loop 3 is not considered a mesh because it contains both loop 1 and loop 2. So that's the distinction between loops and meshes. So before we move on to our next topic, does anybody have any question about these 7 definitions that I've outlined here? All right. So now that we have some understanding of basic circuits terminology, I want to introduce, I want to do an example problem first that I forgot about apparently. So this guy is going to be a little bigger and a little uglier. So let's consider the following circuit. Thing won't write. There we go. All right, so this is a bit nastier looking circuit than the one we just dealt with. Let's start by identifying how many nodes there are. Anybody care to venture a guess? All right, nobody's saying much of anything, so I'll just start identifying some. So we have one node right here that connects elements A, B, D, E, and F together. We have a second node here connecting elements F and G. We have a third node here connecting elements B and C. Here's a fourth node connecting A, C, D, E, and H. And here's a fifth node connecting elements H and G. Are there any other nodes that I've missed?
No, sir.
No.
Nope. All right, so there were 5 nodes. Which elements are in series? Anybody care to venture a guess here?
F and G and H.
So F and G are in series. G and H are in series, and we can absolutely consider that all 3 of them together as one series combination. So we could say that F and G and H are all together in series. I got no problem with that. Any other elements in series?
B and C.
B.
Yeah, B and C. Yep, B and C. All right, so that's all of the elements that are in series. Let's see. Which elements are in parallel? This is a little bit trickier. Anybody have any thoughts?
A and D.
A and D, all right. So A and D is correct. A and D both share the blue node and the purple node, but there's actually one more element in parallel with those guys.
D and B.
E.
Yeah, so B is not in parallel because while they do share the blue node, they don't share the purple node, right? The bottom terminal of B is connected to that pink node, not the purple node. I believe somebody said element E, which is correct. So elements A, D, and E all share the blue node at the top, and they all share that large purple node at the bottom. So they are all connected in parallel. One other question. How many meshes are there? So recall that a mesh is a loop that doesn't contain any smaller loops.
4.
4, right? So here's one. Here's a second one. Here's a third one. And here is a fourth one. I'm not going to go through all of them, but there are actually 10 different loops in this pretty simple and straightforward configuration, and it will take us a little bit of time to identify them all, which is why I'm not going to do it. But as an exercise to you guys, I would encourage you to go through and try to identify at least 6 or 7 of them. So there were 4 meshes. Okay. So now let's introduce some basic electrical quantities. All right, so the first quantity that I want to talk about is voltage, okay? Voltage is the electrical quantity that we're probably all the most familiar with. Anytime that we've had to change the batteries in a remote control or jump start a car or something like that, we've been playing around with voltages, so to speak. Today, we are going to introduce a more formal description that will aid us in our development of circuit analysis techniques, okay? So mathematically, voltage is defined as the line integral of an electric field vector dotted into a differential line element. So mathematically, voltage looks something like this. So while most of you guys are probably pretty familiar with line integrals because you've taken Calculus 2, you may be significantly less familiar with the concept of electric and magnetic fields and all that kind of good stuff. And that's perfectly okay. We're not actually going to use this mathematical description of voltage very often in this class. Really, we're going to use it today to generate two definitions for voltage. And then we're going to use it again tomorrow to formally introduce Kirchhoff's voltage law. And from that point on, we are going to be good enough with our voltages, okay? So the electric field, E, here, which again, I know that you guys aren't super familiar with, is related to what's called an electrostatic force by a simple expression. Okay, so the electrostatic force, Fe, is simply Q charge multiplied by an electric field. We can rearrange this guy, and we find that E is simply 1 over charge times our electrostatic force vector. So if I substitute this in, I get the line integral from A to B of 1 over Q force dotted into my differential line element DL. And since charge is a constant term, I'm going to pull that to the outside here. And I'm left with this mathematical expression. So now here's a question. Who paid attention in physics class and recognizes that integral? So ignore the 1 over Q part. What is the integral of force dotted into some differential line element?
Work.
Work, exactly right. So that leads us to our first definition for voltage, okay? All this ugly equation really represents is that voltage is the amount of work required to move charge from point A to point B in a circuit. So it's the work or energy per unit charge required to move 1 coulomb of charge between 2 points in a circuit. Now, this definition is important, but we're actually not going to use it very much. So let me talk about why it's important, okay? This definition is what tells us that voltage is the quantity that provides the push that makes electricity flow in a circuit. So without voltage being present in a system, we actually don't observe any flow of electricity. The voltage, also commonly referred to as an electromotive force, is what's causing energy transfer to occur, which is in turn driving electrons around the circuit, okay? Now, if we look at our line integral representation again, we can also determine a second definition for voltage, okay? And this one is actually fairly straightforward just by understanding what a line integral is. And also it helps that we know what work is. So I can say that this voltage VBA is simply the voltage VB minus the voltage VA, because a line integral like we have here for a conservative force, which is an electrostatic force, is really just saying that it's the difference in electric potential between two equipotential surfaces. So very, very similar to what we did, or what you guys did way back in Physics 201, but now we're applying it to an electrical system. So our second definition for voltage, and this is the one that we're going to use a whole heck of a lot, is just that voltage is the difference in electric potential energy between 2 points in a circuit. Does anybody know what the unit of voltage is?
Volt?
Volts, absolutely right. So 1 volt, which is the fundamental unit for voltage, is defined as 1 joule per coulomb. And this comes directly from our first definition because it is the energy per unit charge. Energy being measured in joules and charge being measured in coulombs. So in a circuit, voltages are defined by their magnitude and their polarity. And we can do this in a variety of different ways. So I'm going to draw 3 small diagrams here. So we have a generic circuit element, another generic circuit element, and over here, a third generic circuit element, okay? So the first way that we can represent voltage in a circuit is what's called a double subscript notation. So in a double subscript notation, I identify terminals with subscripts. So I'm saying that the top terminal has a label of B, and the bottom terminal has a label of A. And I could say that the voltage VBA is equal to 5 volts. So what this means is that terminal B is at a potential that is 5 volts higher than terminal A. Okay. This notation method is used a lot in very complex circuits and is used extensively in a concept called three-phase power, which all of you electrical engineering students will have to deal with when you take circuits 2 in the winter or spring, whenever you get around to it, okay? Outside of kind of specialized electrical engineering, the double subscript notation isn't used that much. There's two, I would argue, simpler notations that'll be used that we'll discuss in a moment. One thing that's interesting about the double subscript notation is that, by definition, VBA is VB minus VA, and we could say that VAB would then be VA minus VB, which is just negative VBA. So we can represent the exact same voltage, VAB, as negative 5 volts here, okay? So if we change the order of the subscript, that is the same as multiplying the magnitude of the voltage by a factor of -1, okay? Our next notation method, I'm going to call the American voltage sign convention. That's the one that we're going to use in this class. In the American voltage sign convention, we label our component with a particular voltage drop. So in this case, I'm just using 5 volts as an example. And we assign a plus sign to the polarity at the higher electric potential and a minus sign at the terminal associated with the lower electric potential, okay? If we were to change the polarity, our new voltage would be considered the negative of our original voltage, okay? So this 5 volts on the left-hand side with positive polarity on top is exactly identical to the negative 5 volts that we have on the right-hand side with positive polarity on bottom. So some of you, when you took engineering 120, 121, and 122, when you measured the voltage drop across a resistor, you may have found that the voltage drop was negative. And if you changed the leads on your multimeter, you would observe that the voltage changed to be positive. That is this exact same thing. If we change the polarity, we change the sign. This is the convention that we are going to use in this class, but because I know that people like to supplement my lectures with watching videos on YouTube and stuff like that to try to figure things out, I want to introduce also the European voltage sign convention because there are a lot of videos and stuff that use it. So in the European sign convention, we might have something like this, where it's done with arrows, okay? So the same thing, our voltage is 5 volts. The head of the arrow is associated with the positive polarity terminal, and the tail of the arrow is associated with the negative polarity terminal. This voltage is identical to this voltage. V is equal to -5 volts. So if we change the direction of the arrow, that's the same thing as changing the sign on the magnitude, which was the same thing as, say, changing the polarity for our American sign convention, okay? So to be clear, this guy here in the middle is the one that we are going to use for, I would say, 99.99% of this class. So before we move on to voltage sources, does anybody have any questions about these conventions? All right. So we are going to be dealing with lots of different types of voltage sources in this class. All right, the first one is the one that you're likely the most familiar with. This guy right here represents a battery. It was used extensively on all of your exams and stuff like that, way back in engineering 120 and 121. For a battery, the longer line represents the positive polarity terminal, and the shorter line represents the negative polarity terminal. So I'm just going to put here Vs. A battery is an example of a DC source, meaning that the voltage provided by the battery does not change in time. The voltage source representation that is going to be used the most in this class is the generic DC voltage source. So it does the exact same thing as a battery, okay? It just provides a constant amount of voltage that does not vary with time. The positive or the plus sign in the circle in the middle is associated with the positive polarity terminal, and the minus sign is associated with the negative polarity terminal, okay? So practically it is identical to a battery. It's just a more generic form. So a battery symbol is technically only used in a real schematic diagram representing a circuit whenever there is physically a battery present. But if you wanted to use a DC power supply, like we'll be, or I say we, I'll be using to do all the labs for this class, that would be better represented by this generic DC voltage source. Our third symbol is going to look very similar, but we're going to put a squiggle here in the middle of it. And this is representative of an AC voltage source, okay? So what the AC voltage source represents is a voltage that varies in time, okay? So typically speaking, this is classified as sinusoidal voltage sources, which we'll be dealing with a lot in the last third of this class, but it can be also used to represent square waves, triangular waves, or really any time varying voltage signal. Okay. Now these three representations are what are called independent sources. Okay. In an independent voltage source, the value of the voltage, so let me write here, this is V of t, the value of the voltage present across the element terminals does not depend on any outside quantity. Okay, now right now that may not make a heck of a lot of sense, but I'm going to introduce two more voltage sources that'll make this seem a little bit more clear. The first of which is going to be this guy, where I'm going to call this quantity K Vx, okay? This is what's known as a voltage controlled voltage source, all right? And this quantity K has units of volts per volt. This is what's called a dependent source. And what that means is that the voltage present across this voltage source depends on that voltage Vx, which is going to be a voltage somewhere else in the circuit. These dependent sources that we're going to be dealing with in this class cause quite a bit of confusion among Circuits 1 students, typically. And I think the biggest reason is that not enough attention is paid to the units of the modifying coefficient here. So let me explain how a voltage controlled voltage source might work, all right? Let's say that we have a simple circuit where we have a dependent voltage source that's providing us 10 volts. Here's some element A. Here's our dependent source. Here's some element B. And here is some element C. I'm going to define the voltage drop across element C to have positive polarity on top, negative polarity on bottom. So I'm just using the American voltage sign convention here. Well, my dependent source might provide a voltage of 5 VC, meaning whatever voltage drop occurs over element C between this terminal and this terminal, there will be exactly 5 times as much voltage being provided by this dependent source. Okay. Dependent sources are used to describe the way that amplifiers behave, and they're also used a lot in describing or simplifying transistor circuits. So we're going to get our feet wet with them here as just kind of an abstract quantity where the voltage provided by this source is dependent on some other voltage present in the circuit elsewhere. And then those of you that continue on in electrical engineering will get a lot more detail about how and why dependent sources are applicable. We also have another type of dependent source. It has the exact same symbol. Okay, so that's another place that can be a little bit confusing. And the voltage present across this voltage source is dependent on a current, Ix. So this is called a current controlled voltage source, okay, where this coefficient R has units of volts per amp, okay? So these guys are dependent voltage sources. And a current controlled voltage source might be something like this. So let's say that we have practically the same circuit. I'm getting a little bit ahead of myself here because we haven't talked about current yet. But I'm going to say that I have some current IC that flows through my circuit element C with this particular direction. My dependent voltage source now provides 5 times, or 5 volts per amp times the amount of current that's flowing through element C, okay? So that 5 implicitly has units of volts per amp, so that when I multiply 5 times that current, I get a voltage, okay? So that's a point where a lot of confusion occurs. So I just want to be very, very clear about that. So the coefficients, or excuse me, the units for the coefficients for these dependent sources is very, very important to being able to apply them in our circuit analysis. Okay, so we've talked an awful lot about voltages. Does anybody have any questions before we move on to currents? All right, nobody's saying much of anything. So our next quantity then will be current, and to a lesser constant charge, okay? So current is mathematically defined as the derivative of charge with respect to time, okay? Which is going to lead us to our first definition. Current is defined as the time rate of change of charge flow along a path, all right? A second definition for current, which is one that was probably more used in your Engineering 120 series, is that current is the amount of charge that passes a point in a circuit per unit time, which gives us rise to our units for current. The unit of current is 1 ampere, and an ampere is fundamentally 1 coulomb per second. Okay. And it's, like I said before, it's likely that this second definition is the one that you're probably the most used to. But now that we've had a bit more calculus than we had in Engineering 120, our more formal definition is that of a derivative-based relationship. If we use a little bit of math, we can develop a relationship for the amount of charge based on current. So if we multiply both sides by dt and integrate, we find that charge is equal to the integral of the current Ix dx when we're integrating from some time t naught to some later point in time t plus q e naught. So let me explain what's going on here in this equation for charge, because it may not be intuitively obvious, all right? The first thing that I want to point out is that I am using x as a dummy variable for time, okay? So x is still representative of time. My limits of integration are from t naught to t. So that t naught really just means some point in time where the amount of charge that was stored or flowing into the circuit element, etc., is a known or fixed quantity. And then t is representative of just some later point in time that we're interested in, okay? So, for example, let's say that problem here. The charge Q of t is equal to Im multiplied by t plus Qm sine omega t, where Im is equal to 6.3 milliamps QM is equal to 2.1 millicoulombs, and omega is equal to 1.3 radians per second. If I wanted to determine the current flowing through this circuit element at a time t is equal to 700 milliseconds, how would I go about determining that quantity?
You need to differentiate Q with respect to time.
Yeah, so we use the equation that we have up here on the left. You're absolutely right. So we could say that I of t is equal to dq by dt. So that's going to be d by dt of Im t plus qm sine omega t. So the derivative of the first term is going to be just Im, right?
Yeah.
The derivative of my second term, what's that going to be?
It's going to be QM cosine WT.
It'll be omega. You were right the first time. QM cosine
WT.
omega t. Right, got to use the chain rule there because there's there's something multiplied by t inside of the sine function. Using the chain rule tells us that we should have that guy pop out. Then we would evaluate this guy at exactly t is equal to 700 milliseconds, which I'm going to call 0.7 seconds for reasons that'll be obvious in just a second. So I of 0.7 seconds is going to look like 6.3 milliamps plus omega, which is 1.3 radians per second, times QM, which is 2.1 millicoulombs. Yeah. 2.1 millicoulomb times cosine of omega 1.3 radians per second times 0.7 seconds. So I knew that my omega was measured in radians per seconds, which is why I converted t into seconds. Another thing that I want to point out here just real quick. So I have a millicoulomb per second when I multiply this guy and this guy together. A millicoulomb per second is the same as a milliamp. So I'm adding milliamps plus milliamps. I have the answer to this problem, but I want you guys to calculate it if you have a calculator handy and tell me what the answer is, because I'm willing to bet that I'm going to get two different answers.
7.98.
All right. Mr. Gray says 7.98 milliamps. Did anybody else get something different? All right. Well, you guys are much smarter than my, let's see, actually, hold on here. 23.055, okay? Not the other answer that I was expecting, but I might have punched something into my calculator wrong. So let's talk about which of the answers is right. So I'm going to put 23.055 milliamps here. All right, now, Mr. Gray, I'm going to ask you probably an odd question, but how is your calculator set up? And what I mean by that is, are you using, is your calculator in degree mode or radians mode?
That's in radians. I double checked it because the first time I did it in degree and got like 9 point something.
All right, so 9 point something is what I got as well, right? So it is very important in this class that anytime we are dealing with omega, and it's going to be a whole heck of a lot, omega is defined as radians per second, which means when we multiply omega times a time value, our angle is in radians. So we need to make absolutely sure that we get into the habit of doing calculations in radians mode, okay? So for this particular problem, there's going to be an answer if you do it in radians, which is correct. And if you do the exact same calculation, but you forget to turn your calculator from degree mode into radian mode, you're going to get an answer of 9 point something. That is not right. Okay, so I just want to be explicit about that. And the reason why I do this particular example problem is because there's going to be people who attempt the web work and are approaching the problem in the absolutely correct way, but are getting the wrong answer, and it's because you're using degrees when you should be using radians or vice versa. So you got to pay attention to the units on literally everything in this class, or there's going to be little things like that that'll bite you in the butt and just frustrate the heck out of you. All right, so this level of calculus, taking a simple derivative of a sinusoidal function, is really about the maximum level of detail or the maximum level of calculus that's going to be needed to be successful in this class. We're going to be integrating and taking the derivative of sinusoids and exponential functions, and that's pretty much it. So for the most part, all of the calculus that's required in this class can be done really using your calculators. Hopefully you guys know that your TI-36s and your Casio FX115s can do simple derivatives at a particular value and simple closed intervals. All right, let me do another problem real quick here relating current and charge. All right. This is another way that I like to ask questions on a test. So let's say that I have the following graph. Okay. On my vertical axis is my current as a function of time measured in milliamps. And on my horizontal axis is time measured in seconds. I have a waveform that looks something like this. Where this value corresponds to 10 milliamps. And this value here corresponds to 10 seconds, okay? Our goal is to determine the amount of charge that is passing through a circuit element over the time interval. So we're looking for Q over the time interval 0 less than T less than 20 seconds. And we are told that the charge entering our circuit element at T is equal to 0 is negative 25 millicoulombs. How would we go about approaching this problem? So the first question I want you guys to answer is, should I use the first equation or the second equation that we've developed in this section? So do we use this guy or this guy? Let's see what chat's saying. The integration one, absolutely correct. Okay. So our integration equation says that Q T is the integral from T naught to T of I of X dx plus Q T naught. Okay, that is our equation. One thing that I didn't point out earlier, but I probably should have, this guy Q right here, excuse me, is not inside the integral. Okay, so it just represents an initial condition on the system, so we do not integrate it. Now, I have the means by which to set up this integral, right? I have a piecewise function that I could use to describe my current waveform. I could substitute that in. I know what the initial condition on my element charge is. However, that would be the most complicated way to solve this problem. Who can tell me what an easier way to solve this guy is than mathematically doing the integration? Area under the curve, absolutely correct. All of the graphical methods that we're going to use in this class will be based on, or all of the graphs that I present to you and make you analyze will be based on simple shapes like rectangles, squares, and triangles. So this integral part right here is simply the sum of this guy, which I'm going to call area 1, and the sum of this guy over here, which I'm going to call area 2, plus our initial condition, right? So what is area 1? So it's a rectangle. Can we agree on that? Or what's the equation for the area of a rectangle?
10 milliamps times 10 seconds.
Yeah, 10 milliamps times 10 seconds. All right, so that is A1. What is area 2? What's the equation for the area of a right triangle?
1/2 the base times the height. So
Right.
1/2 times 10 milliamps times 10 seconds.
So 10 milliamps is the height, and then 20 seconds minus 10 seconds, and I had to hurriedly draw in 20 seconds there because I forgot to label it. So the base of the triangle is 10 seconds wide. What is Q at T naught in this case?
Minus 25 millicoulombs.
Yeah, so the negative 25 millicoulombs. All right. So if we add all of these things together, we have 100 plus 50 minus 25 is 125 millicoulombs, which is the exact answer that we would get if we went through the painful, and it's not really that painful, amount of math to derive the piecewise function that describes our current waveform, and then apply time shifting theorem and all that kind of good stuff. So area under the curve, for the most part, you should always just do it using simple area relationships. Squares, rectangles, and right triangles are all you're going to see in this class. If it's something else, I will literally tell you exactly what it is so that you can just use the calculus method to do it. All right. So we've worked a couple of examples relating current and voltage. Now let's talk a bit more about how we represent current in a circuit. All right. So if we have a generic circuit element, like so, we represent current with an arrow. So current is, in an electrical circuit, current has both a magnitude and a direction, okay? So we might say that the current I is equal to 5 amps, and it has a direction of down, so it's flowing from top to bottom. And this is the exact same thing as a current I having a direction up of -5 amps, which when you measured current in your engineering 120 series, you may have noticed that sometimes you got a negative value, and if you flip the leads on your multimeter, it made it positive. That is exactly why. You're effectively just changing the direction of current flow through your multimeter when you swap the leads around. There is no difference between the American convention and the European convention. It's always just a number telling you what the magnitude is, and then an arrow telling you what the direction of the current is. There is technically a means by which to do a double subscript notation for current as well, but I absolutely never use that in this class, so I'm not going to bother introducing it. And I haven't seen a YouTube video that uses it other than those talking about three-phase power, which is well beyond the scope of this course. All right, so we've talked quite a bit about current these last several minutes. Does anybody have any questions about current and charge?
No, sir.
All righty. Well, let's move on to our last couple of topics then. And these two quantities are related to each other. We are going to talk about power and energy. Okay. All right. So power is mathematically defined as the derivative of work with respect to time. That is the classical definition that you guys have all dealt with in your Physics 201 class. We can actually expand this bit a little bit further by saying that power is the derivative of work or energy with respect to charge multiplied by the derivative of charge with respect to time. And we can recognize that derivative of work with respect to charge is simply voltage, and the derivative of charge with respect to time is current, giving us the relationship that power is simply the product of voltage and current, which is exactly what you guys learned back in your engineering 120 series. Okay. With regards to a formal definition, we will say power is the rate per unit time at which electrical energy is transferred to or from a circuit element. All right. Since it's the rate per unit time at which electrical energy is transferred, its unit is the watt, which is defined to be 1 joule, the unit of work or energy, divided by 1 second, which is our fundamental unit of time. All right. So this should line up pretty much exactly with what you guys covered in the 120 series. Now let's talk about energy. Kind of have a circular relationship here. For our class, energy will be simply the integral of power. Where we integrate from one time of interest to a second time of interest. Where did my eraser go? Let me make this T look a little bit better. Okay. And our definition for energy is the total power transferred to or from a circuit element over a fixed period of time, where energy has a fundamental unit of joules, and we're not going to break down a joule into anything else because that is one of our fundamental units for electrical quantities. Okay, so that is our mathematical and word-based definitions for power and energy. Okay. Power and energy are very, very important quantities in electrical circuit analysis, so much so that we have to adopt a very specific convention in order to make sense of them. So I'd like to talk about that real quick, okay? So what we're going to be talking about for the next few minutes is what's known as the the passive sign convention. All right. So let's say that I have a generic circuit element like so, where I've intentionally elongated these terminals for us to look at something, okay? Let's say that my voltage has this particular polarity, positive polarity terminal on top, negative polarity terminal on bottom. And my current, I, is flowing into the positive polarity terminal. Okay? Under this convention, we say that the element is absorbing P is equal to V times I amount of power, or we could say that our element is supplying P is equal to negative V times I amount of power. Okay. So So if V and I were both positive quantities, or both had positive magnitudes, then we expect that when the current flows into the positive polarity terminal, we get a positive amount of absorbed power and a negative amount of supplied power. Now let's consider this, and so how I like to depict that is that power and energy are flowing into the element. Now let's look at the opposite perspective. We have our generic circuit element, but now I'm going to define the positive polarity terminal for the voltage to be on bottom. And we're still going to have our current now flows into the negative polarity terminal. In this case, our element is absorbing E is equal to negative I times, or V times I. I guess I'll use V times I because that's what I've been using. Amount of power, or we consider it to be supplying P is equal to positive V times I. This is something that is going to potentially trip students up who aren't paying attention for literally the entire duration of this class, and if you're an EE student, for the next couple of years, okay? It is a very simple concept, but it's also very simple to overlook as well, okay? So the passive sign convention says that when the current is flowing into the positive polarity terminal, we are absorbing power. And when the current is flowing into the negative polarity terminal, this is what we consider to be supplying power, all right? So I would typically depict that as current, or excuse me, the power is flowing out. This is W and not E, since we're using W as energy. All right. So to beat this into your skull, because it is literally that important, you'll be super frustrated with lots of homework assignments, test questions, and all that kind of stuff if this doesn't make sense. Let's look at a very simple circuit. All right, let's do it here. So this is going to tie a few things together, hopefully. Okay. So let's say that I have the following circuit. I have a 30-volt source like so. I have a dependent source. And here's some other information that's provided to us. The voltage drop over element 3 is 28 volts, positive polarity on top, negative polarity on bottom. The voltage drop over element 2 is 24 volts, positive polarity on top, negative polarity on bottom. The voltage drop over element 1 is 12 volts, positive polarity on the left, negative polarity on the right. And let's say that my current IX is 4 amps. Actually, let me draw this better. And it is defined to be this current flowing through element 1. I have a current of 2 amps flowing down through this guy, a current of 2 amps flowing down through this guy. Let's call this a current of negative 2 amps in this direction, and this guy a current of 4 amps in this direction. I want to determine the power absorbed by each element. All right. So let's start with my 30-volt source. Okay. So what's the voltage drop across my 30-volt source? Not a trick question.
30 volts.
30 volts. Okay. What's the current flowing through my 30-volt source?
4 amps. Oh, it's going into, yeah. 4
All right.
amps.
So the current is going into the positive polarity terminal or the negative polarity terminal.
The negative, so negative 4 amps.
All right. So I put a negative sign out front. The power absorbed is then negative 120 watts. Does anyone need an explanation of where that negative sign came from or those numbers came from? Do not feel embarrassed if it's confusing, okay? I have senior EE students who still make simple mistakes on this very regularly. All right, this is one of the things that is going to pop up again and again and again. I can't tell you how many times, even in week 9 of this class, I still have to go through and talk about the passive sign convention and what it means to be absorbing power and what it means to be supplying power. So if it's confusing at all, by all means, ask a question.
So Dr. Hartman, the power is absorbed because the current is going through, but you have to add the negative sign because it's going into the source through the negative terminal.
That is exactly right. So the negative sign is because the current is flowing into the negative terminal, and we are trying to determine the power absorbed by each element. If we wanted the power supplied, it would just be 30 volts times 4 amps with a positive sign, because if we look here at our convention, when the current is flowing into the negative polarity terminal, P is equal to V times I for supplying, and P is equal to negative V times I for absorbing. All right, let's look at the element 1. Somebody else tell me what's up. Our voltage drop is across this element is what?
12 volts.
Our current flowing through this element is what?
Positive 4 amps.
All right, and is the current flowing into the positive polarity terminal or the negative polarity terminal?
No, positive.
Positive polarity terminal, okay? Because we are calculating the absorbed power, that means that we have a positive sign here. So we simply multiply 12 and 4 and we get 48 watts. Element 2, somebody else tell me what's going on here. What's my voltage?
$24.
24 volts, all right. And Mr. Menendez, what is my current?
That'd be 2.
2 amps, all right. Is the current flowing into my positive polarity terminal or my negative polarity terminal?
I'd say positive.
right? It's flowing into the positive, which means we'll have a positive sign here. So we have 24 times 2 is another positive 48 watts being absorbed by element 2. Now let's look at our dependent source, which is going to be a little bit more tricky, okay? What is the voltage drop across my dependent source? So based on what the circuit diagram tells me, the voltage drop is 1 times Ix, okay? But we have to remember that this is a voltage controlled, excuse me, a current controlled voltage source. And actually, I forgot to talk about something kind of important, so we'll have to circle back around to that in just a minute. I can't believe I forgot it. All right, but so we have a current controlled voltage source, which means that that 1 has units of volts per amp. So we have 1 volt per amp multiplied by Ix, which has a value of 4 amps, which means 1 volt per amp times 4 amps is simply 4 volts. Yeah. Current flowing through our dependent source is -2 amps. And the current is flowing into the positive polarity terminal. So that means we should have a positive sign here, giving us -8 watts being absorbed by this dependent source. Our last element, element 3, we have 28 volts across it, 2 amps flowing into it, and the current is flowing into the positive polarity terminal. So we have 28 times 2 is 56 watts being absorbed by this element. So somebody do me a quick favor. And add all of these numbers together. Oh, well, that's okay. Well, never mind. Don't do that because I made a mistake. The mistake I made was I couldn't read my example problem. So let me change this real quick and then do it. So this was supposed to be 36 volts, which would give us 144 watts right here. If we added all of these together, we would get a sum of 0 watts being absorbed by the system, which makes perfect sense because if we got anything other than that, then one of our elements would either be creating or destroying energy, okay? So the fact that the sum of all of the absorbed powers, so in a system must equal to 0, or we can adopt the opposite convention, the sum of all of the power supplied in a system must equal to 0, or in a
Q-tips. Trying to really get some Q-tips.
okay, or another way to put this is
That shit pissed me off when I got out the shower. Q-tips.
Taj, your microphone is hot.
Just take a light.
Thank you. The power absorbed must equal the power supplied. All three of these relationships are what is called Telegen's theorem, which is simply one way to express the law of conservation of energy in circuits. So before I go revisit the thing that I was supposed to talk about a little bit ago, does anybody have any questions regarding power, energy, and the passive sign convention?
What is that? The something theorem? I can't read the first word to it.
Okay, I'll write it out less crappily. It is Telegen, T-E-L-L-E-G-E-N''S. It's the last name of a physicist, I believe.
Thank you.
No problem. Any other questions regarding power, energy, and the passive sign convention?
Could you go over one more time how you got the power for the dependent variable or thing?
The
Yeah.
dependent source? Absolutely, yes. So dependent sources are gonna trip you guys up for a little bit, so I'm happy to go over that again. Okay.
Yeah, they are.
The voltage, so let's just call this right here. Let me use a different color real quick. The voltage drop across the dependent source is 1, which implicitly has units of volts per amp. And I can say that because it's a number being multiplied by a current, okay? I know that it's a voltage source because there's a positive polarity terminal and a negative polarity terminal associated with it. So I know that this thing effectively is taking in some amount of current and then scaling it by some factor. So that's where this 1 volt per amp is coming from. So the 1 comes from the fact that there's a 1 written next to it, and the units of volts per amps is what it has to be to make this thing work correctly. All right. So it's 1 volt per amp times IX, where IX is shown in the circuit diagram to be 4 amps. So V dependent, the voltage drop across my dependent source is then 4 volts.
Okay.
All right, then the current is -2 amps because I was told it's -2 amps. The current is flowing into the positive polarity terminal. So I have the 4 volts, which is V dependent, times the -2 amps, which is the current flowing into the positive polarity terminal. And because the current is flowing into the positive polarity terminal, that's where that positive sign comes from. I multiply all that together and I get -8. Sound groovy?
Groovy-ish.
All right. If you have any more questions, we'll be dealing with dependent sources an awful lot in this class. So at any time, just feel free to say, wait, hold on a second. Let's go through this again. Okay. Don't remotely feel embarrassed about it. It's confusing to even me, and I have a PhD in this junk. So.
All right.
All right. So the thing that I forgot to talk about, let me make sure that I forgot to talk about it. I believe I did. Yeah, okay, so we can tuck it in up here, or at least I'll tuck it in up here in my notes. So we talked about the current convention, meaning that currents have magnitudes and directions, but we forgot to talk about current sources in our circuits. Now in Engineering 120 series, you guys likely did not see any current sources whatsoever. So let's talk about how we represent current sources real quick. So our first one that we're going to be dealing with is a simple DC current source. It has a particular magnitude, so we could call it, say, 5 amps or something like that. And the direction of the current is indicated by the arrow. Nothing particularly wild about this. Our second representation of a current source will be effectively the exact same thing, but it has that little squiggle to it, which lets us know that it is an AC current source, meaning that our current I varies with time. These two representations are independent current sources, meaning that they supply a fixed amount of current regardless to what is connected to them. Now, there were two dependent voltage sources, and there will be two dependent current sources as well. The dependent current sources are depicted with diamonds. So the diamond instead of the circle lets us know that we have a dependent source. And then the arrow lets us know that it is a dependent current source. So before, when we had a plus and minus sign, that let us know it was a dependent voltage source. These arrows let us know that we have dependent current sources. The first I want to talk about is a current-controlled current source. So it will just be K times some current IX, where K has units of amps per amp. And so this just means that the current flowing through this source or being supplied by this source is dependent on a current elsewhere in the circuit. And then we also have a voltage controlled current source given by G Vx, where G has units of amps per volt. And so this guy says that the current that is being supplied by this source is dependent on a voltage elsewhere in the circuit. And we'll work on examples for that probably tomorrow, actually, I think. So this is just a little bit about what I forgot, and just to specify, these guys are dependent current sources. All right. I think that is enough out of me for today because I've talked for an hour and 44 minutes straight. So I'm gonna be quiet, and if you guys have any questions for the next couple of minutes, by all means answer them, or I'll stick on and answer them. But if you want to get out of here, by all means do so. Class is over.